أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. Lecture 4, Electronic Devices and Circuit. And in this lecture we will try to understand in-depth knowledge for the forward PN junction and the reverse PN junctions. So these two topics are important, as I said before many times, that these are the fundamental and very basic and very essential topics. We must have to understand these topics very clearly and transparently, so that we can easily grow our knowledge gradually when we advances in this topic. So the letter on lectures might be difficult, but all these will be easier for those who have gone through very clearly, fundamentally, conceptually with these beginning lectures. So lecture 4 is among them. In this lecture, in this lecture we will try to understand the how we can PN junction forward bias, PN junction reverse bias. Although the most of the applications in the circuit we do PN junction forward biased, but the reverse bias is not applied in a number of ways. But however, the reverse bias may be applied in special cases or special applications. So generally, the forward bias is important, but we must have to understand what is the reverse bias and what happens in the PN junction when we do reverse bias. Beside these two topics, the forward bias and the reverse biasing of a PN junction, we will also focus in this lecture to understand the majority carriers in the PN junction and the minority carriers in the PN junction. So the current flow is due to the flow of the majority carriers and the flow of the minority carriers. So we will, having these topics in mind, we will try to understand. Let's we start. First is the forward bias. First, I took this simple circuit, this fundamental circuit. Probably I have shown this circuit before. Here we have the PN junction and the plus of the external supply. This is an external supply, like the supply you have in the test bench in the laboratories. So these supplies are basically variable. You can change from 0 volt to 0.1 volt, 0.2, 0.3, 0.5, 0.6, 0.7, 0.8, 0.9, and up to 1 volt or more if you want. So if the and we know that the PN junction has potential barrier. For silicon, it is 0.7 volt. So when we connect positive terminal of an external supply to the p-type junction, and if we connect the negative supply of the external power supply to the negative terminal of the to the n-type terminal, then then what will happen, then this circuit is known as forward bias. The forward bias is simple, that if we connect plus of the external supply with the positive with the p terminal, minus with the negative terminal, minus with the n-type terminal, then this circuit is known as forward bias. So this is the basic circuit, and this does not provide too much information about the other charges, but we can understand here somewhat on the abstract level, on the basic level, that if the supply, this is a voltage source. This voltage source, let's suppose we take this one. So this terminal is injecting free electrons inside the n-type material. So what will happen? This n-type, there will, at this end there will be more free electrons. That free electrons will diffuse with the positive charge across the potential barrier, across the junction layer. Similarly, this plus terminal of the external power supply injects holes inside the P terminal. This this already have plus holes, and the furthermore this plus hole will diffuse with the electrons near the at the edges of the potential barrier, at the edges of this thin layer. So the more the supply voltage, if we increase the supply voltage from 0.1 to 0.2, 0.3, 0.4, so this supply voltage will inject more electrons here, more holes here, causing the depletion layer reduced, causing the width of the depletion layer is reduced. So what will happen? The more we supply, so for example, if we supply at if the supply is connected at 0.7 volt or greater than 0.7 volt, because this barrier is having electric field of 0.7 volt. If you apply more than 0.7 volt, so what will happen? All these barrier will be removed, and this PN junction material, this silicon material, will have single phase without having any barrier. So this single phase will become a conductor. So the electrons will be injected from here, and it's making a complete loop. So the moment this potential barrier is completely removed, the inrush current will flow from here to here, plus to minus. Always the conventional current direction is from plus to minus. So the direction of the current will be this one. Okay. So and then so the point is that at 0.1 volt, at 0.1 volt, there will be a potential barrier with reduce with reduction in its thin layer. So there will be less flow of current. And as we increase the supply from 0.1 to 0.2, 0.3, there will be more flow of current. But when we break this barrier completely, and we can break this barrier completely at 0.7 volt or at higher volt. So there will be inrush current, there will be maximum flow of current. There we say there will be flood of current. So this piece will become a conductor. The more the voltage, the more we can have current. Okay, what is written here? The forward bias is obtained if the external positive voltage applied to the P type and the negative voltage applied to the N type. Due to this, electrons are forced to inject into the N-type and holes to the P-type, resulting in the diffusion of the depletion layer. And P-N junction becomes the conductor, removing all the electrical barriers. So, as I shown before, if we make a graph of the voltage versus the current. So we apply 0 volt and we can have 0 current. We apply 0.1 volt here, then we can have some milliampere of current flow, 0.2, 0.3, 0.4, 5. If we do, if we draw the graph from 0.1 to 1 volt, having a step of 0.1, then we can see the characteristic of the current flow through this device. And this, if we plot this voltage versus the current flow, then this will be known as the characteristic curve of a PN junction diode. So the PN junction is a diode. So this PN junction, we will next time we will use as a diode, PN junction diode. Okay. Now something. This was on the abstract level, on the basic level, in order to introduce something, uh, uh, fundamentally, conceptually, but it is not the actual figure. So if we want to learn something in depth, then we need to have actual figure. Let's see what happens. Let's take an example of n-type silicon conductor. It should be noted that there are mainly four types of charges in the n-type semiconductor. Remember, there are not only two types of charges as shown as here, the holes and the electrons. Okay, so there are basically in there are four charges. So the two charges, we know this is not the n-type material, but this is the silicon. We want to convert this and this silicon, this piece of silicon. We want to convert this piece of silicon to the n-type material. So I just written here n-type, but this is not in actual now. It is just simple silicon material. So we can have here minority carriers, donor atoms, and the majority carriers. So it should be noted that there are mainly four types of charges in the n-type semiconductor. So we have seen at room temperature, we know at room temperature there will be some free electrons and some free holes. Okay, so this is at room temperature. So these free electrons are directly related with the temperature. If you increase the temperature, these free electrons and the holes will also increase. But let us assume at room temperature this is the condition of the and this is the condition of the silicon. We have free charges. Okay, and for the pure silicon, when at room temperature, minority charges including both free electrons and hole exist. These charges exist, although at very low numbers, but it is there. So they have that is it. These are in very low number. That's why it is known as minority charges. We can we can convert this into more simple. So this is the same block, but here it is shown that which one is the minority carriers. So the whole in this case is the minority carriers and the electrons are the free electrons. Okay, let's see. Because we want to make this silicon piece as an n-type material, so the minority carrier will be positive, will be holes. So now if we dope, because we have to make n-type material, so this piece of silicon we have to dope with the phosphorus atom, which is having 5 electrons at its outer shell. So one of the electron will become free electrons. Let's see more. If added phosphorus atom, then after doping, equal number of negative free electrons and positive charge on the donor atom will be established. Picture shown is post dope. So we have this picture. This picture is basically is after doping, is the result of the after doping. But because we want to show you is bit by bit in different pieces, in small pieces. So I made this one. So this is basically the picture. Picture shown is post dope. If we dope the silicon piece with the phosphorus atom, what will happen? The fifth electron will become free. So these are the free electrons. And because the phosphorus donates one electron, so the phosphorus atom will have positive charge. So this is known as donor atom. So now we can see here we have, if we dope this material with the p-type dopant, then sorry, with the n-type dopant, phosphorus, then there will be two more charges, plus minus plus minus. Remember, the free electrons are free to move from here to here, anywhere. But this charge is not allowed to move, remember, because this charge is the basically positive charge on the phosphorus nucleus, because now the phosphorus nucleus has more proton than the electron because it has removed one electron. So these phosphorus atoms, these ions, phosphorus ions, atomic ions are still having covalent bond with the silicon atom. So and the covalent bond is very strong. So these charges cannot be moved. So the flow of the current is possible by this majority of the free electrons, not by the positive charges. But we should know that there are two more charges, plus, 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 minus. So okay, phosphorus after doping. So this is the donor atom, this is the majority electrons. So if we dope this material with this phosphorus atom, then the resultant charges will be this charge plus these charges. So there will be four charges. That's why I wrote here. It should be noted that there are mainly four types of charges in the n-type semiconductor. Let's see what happens if we. So this is the result of the n-type material after doping. This doping results in two more charges, and this is the final n-type material that we can see. In the final n-type material, we have this plus charge, we have this free electrons, we have this plus charge as a donor atom, the charge on the donor atom, and the minority carrier is holes, because this is having, and this is the also the electron due to the thermal effects. So this electron and this electron will combine with each other, and there will be more majority carriers. So there will be plenty of free electrons. Okay, and this holes is also free to move. So this holes is known as minority carriers. It is the product of the temperature. It is not the product of the doping effect. So this is, I hope you understand. Let's take the same example for the p-type silicon conductor, and we already have said about this thing. For the p-type semiconductor, take again the same crystal, and because we want to make it p-type material, that's why I written here p-type, because we have to convert it to the p-type material. But this time it's not the p-type; it's just a silicon material with having, because at room temperature this will have minority charges, the free electrons and the holes here. So if you transform this one, so we can see here the p-type material will have minority charges, because the p-type material will have holes as a majority charges. So, and this p-type material also has this free electron. So this free electron will be known as the minority charges. Okay. So this is the try to understand the differentiate between the minority charges and the majority charges due to the thermal effect and charges to the doping. So boron after doping, so we have to make p-type materials. We must have to dope with the p-type dopant, that is here it is boron. So we can see in the boron, because boron is having short of one electron, so the covalent bond of the silicon will give one electron to share with the boron atom. So the boron atom will have a negative charge. Okay, so the acceptor atom here, because the boron atom accepts one electron, so this is an acceptor atom, and because one electron is free from the structure, so the equivalent number of holes will also be created. Okay, as we seen before. If added boron atom, then after doping, equal number of positive holes and negative acceptor atoms will be established. Okay, so these are the result due to the doping of the boron. Picture shown is post dope. Yes, so doping results in two more charges. So here we can see, because of the doping there will be two more charges. One, the charge with on the boron atom, negative, and there will be majority carrier as whole. You can see. So these are the after doping. Uh, this picture shows after doping. So we have to combine this one with this one. So in total, we will have again 4 charges here. So this is the final type of the p-type material. It has 4 charges. And in this case, you must have to understand which is the majority carriers. So in this p-type material, holes is the majority carriers, and the negative is the charge on the boron atom. It's known as the acceptor atoms, and this is not going to play, going to play, going to contribute in the flow of the current. So this is not going to be effective for the flow of the current, but this is the negative charge we should know. And the flow of the current is possible with the majority carriers, that is plus holes, and the minority carriers here is because this is the p-type material. It has plenty of holes, plus holes, and it has also free electrons, and this free electron is known as minority carriers. And this free electrons we should know is not the effect of the doping, but it is the effect of the thermal. It is the thermal effect. Hope you understand. Now we combine these two material, and we will put all the possible charges, all the 4 charges. So here, this state shows that we have a silicon crystal. At one end, it's p. If we are going to top with p-type material, we are going to make a p-type material here, and this at this end we want to make it n-type material. But at room temperature, we can find some free electrons and the holes, as we have seen many times. But the p-type material has minority carrier as free electrons. The free electrons are the minority carriers of the p-type. And remember, these holes, plus holes, are the minority carriers for the n-type material. Okay, let's move the p-n junction depletion layer. So this is the figure which I split it in the previous 2 slides, and now I combine this picture. So here the p-type material, in the p-type material, majority carrier is holes, minority carrier is free electrons, and n-type material, minority carries is plus, and majority carries is free electrons. Okay. What happens soon after the doping? We start, because this is a single silicon crystal. So after doping, the majority carries here, electrons will try to move from this side to this side because it has plenty of holes. So this will move right side, left side, and the holes, it has plenty of holes and it has plenty of electrons, so the holes will try to move here. So what will happen after diffusion of free electrons and the free holes? There will be an equilibrium state, and under this equilibrium state, there there will looks like a electron cloud, and there looks like a holes cloud. So this two will make like this two will not allow further migration of the electrons from here to here, from one end, or holes from one end to another end. So this will stop further migration, and this itself will make an isolation, will make the piece of this silicon material an insulator, because this is not going to allow the free movement of the charges either side. Hmm? So this is the depletion layer, and depletion layer is that region where non-mobile ions are present, that is no mobile charge is there, and this region is formed due to diffusion of negative and positive ions across p-n junction. Barrier potential is the potential drop which is formed as a result of diffusion of ions and then formation of depletion layer. The first semiconductor device, the first semiconductor device now can be constructed by the simple p-n junction that was developed in the previous slide. So yes, this is the p-n junction. This is known as the diode. So the diode can be made by this simple p-n junction, and it has in between it has a potential barrier or thin layer. So applying external voltage, so how we can make a flow of current, we can apply an external voltage here. If we connect this material, if we connect plus, if we connect plus of the supply to the p-type material and the minus of the supply to the n-type material, means plus to plus, minus to minus, then this circuit is known as forward bias. So we can say that diode is in the forward bias region. So applying external voltage to the PN diode start to reduce the width of the depletion region. So we will start from 0 volt, 0.1 volt, 0.2 volt. So it will start to reduce as we increase the voltage, the depletion layer will reduce. Depletion width will reduce, and when we cross the 0.7 volt or beyond the 0.7 volt, this will completely remove and this will become a conductor, as we discussed before. It should also be noted that okay, the main point here is that the diode, because this is going to become a conductor, so the flow of the current is from plus to minus. So this flow of the current is known as ID, diode current. So the current is diode current, but this current is composed of two different currents: current due to the majority charges and current due to the minority charges. Okay, so let's see. Because this plus, this is the whole, this is pushing, this external supply is pushing hole, and these holes are combined, diffuse with the electrons. Similarly here, this is penetrating, this is injecting electrons, and this already have free electrons, so these will combinedly diffuse with this one. And if we move, if we apply enough voltage, then this depletion layer will finish. Okay, so the current will be the majority of the current will be due to these free electrons and these free holes. So that's why it has the I majority is we have shown longer. So the main current is the ID. The main current of the ID is due to the flow of the majority charges, but there still exists some minority charges. So here the minority charges in the n-type material, these are the free holes. These are the free holes. So these are the minority charges, and in this p-type material the minority charges is electron. These free electrons. So this will also move, but this will move in opposite direction. Plus will move from this side to minus. So the majority current was from left to right, but the current due to the minority charges is from this side to this one. So that's why I have shown the different direction, and this is much less than this one. Okay, so the net diode current will be this one minus this one, I majority minus IS. It should also be noted that in the p-type crystal there exist electrons as minority carriers. Thus, due to movement of this minority charges, current moves in the opposite direction and known as IS. So the current due to this minority charges is known as IS, the reverse saturation current. This is known as reverse saturation current. ID is the net diode current, while diode voltage at VD. So this is the Shockley equation, and it's used is this is the equation for the diode, for the diode current, for the diode voltage, for the diode reverse saturation current. So this equation represent the characteristic of this p-n junction diode. And this equation is valid if the diode is in the forward bias or if the diode is in the reverse bias. It does not make differences. So this is the equation for the diode. So here ID diode current, as I've shown here, and I is the reverse saturation current. And remember, reverse saturation current is due to the flow of the minority charges. VD is the diode voltage at this point, voltage at this point, and in this case, this point is directly connected to the VD. This point is directly connected to the VD. So the diode voltage is also the VD. N is the material constant here, the process constant of the p-n junction is known as ideality factor. It depends on the construction process, means manufacturing process, and the material quality. For example, the material can be germanium, material can be silicon, material can be others. So it depends on the manufacturing process and the property of material. Its value ranges from 1 to 2. In some cases, it exceeds from 2 value as well. So the as the name implies, ideality factor, if this is 1, if n is equal to 1, then it means that diode is ideal. Okay, so for ideal diode n is equal to 1, and I suppose that throughout this course we will use the ideality constant as equals to 1 for the sake of the simplicity. Hmm? Okay, now p-n junction reverse bias. So if the diode is made and it is not connected with any external voltage, we know there is an electric field which opposes further flow of the charges. But the reverse bias is if we connect this p-type material with the negative supply and the n-type material with the positive supply, then the diode is said to be in the reverse bias. What happens if the diode P terminal is connected with the negative supply? Okay, if the diode P type terminal is connected with the negative supply and N terminal, this is N terminal is connected to the positive supply, then this diode connection is known as reverse bias. Let's study more about the reverse bias. We can see here in the reverse bias, okay, first we can see the depletion layer is going to widen. So depletion layer here is thin, and after supplying the reverse voltage, the depletion layer width is increased significantly. Why it is increased? Because we are connecting minus charge, minus terminal. This is having capability to inject electrons inside this material. So this electron will accumulate further on here. So making more wider layer in this portion. Similarly, this has capability to inject holes. So this will inject holes, and because it's also already having the holes here, so the more holes will accumulate here. So the result is that the thin layer will become wider than it was before. So under the reverse bias condition, the depletion layer is widened, yes, and the majority current. We know that here, if this was the uh, thin layer, and if we this thin layer can be broken, removed by applying a forward bias, as we have seen in the last slide. But we are not providing this type of forward bias. We are providing opposite connection of the supply. So this is causing the increase in the width layer, increasing in the in the in the width of the layer. So this what we are making, consequently we are, this still will not the allow the movement of the majority charges. This also does not allow the movement of the majority charges, but because we have strengthened the width of the thin layer is more strong now, so there definitely there will be no flow of the majority current. So the current due to the majority charges is zero. So current due to majority carrier is zero. We know that minority electrons at p type, we know that at p type we have minority electron, this I shown here, and minority holes at n type exist. So minority hole at it also exists. So what will happen? This plus will push this plus, and this minus will push this minus, this minus. So it's possible that there will be some flow of charges, but this time the flow of charges is from this direction to this direction. So the is minority carrier flow is in this direction, is in the opposite direction, and the majority carrier is significant, it's significantly zero. Sorry, it's approximately zero or almost zero. So we have seen here the conclusion is that if we supply the if we connect the PN junction in reverse order, I mean in with the reverse polarity, then there will be no majority current, but there will exist very small amount of minority current. This is the conclusion of this slide. We have to read something more. The reverse biasing forces these minority charges to move from one end to other end, and thus current due to the minority carrier flow as Is. So Is is the only current. In normal operation, Is remains in the range of nanoampere or the microampere. So generally, Is is small enough that it is ignored in the majority of the circuit analysis. So in general applications, yes, we do ignore the is the majority, and we say that okay, in the reverse bias condition there is no flow of current, there is no flow of majority charges, there is no flow of minority charges. So we just say that okay, this is, and there is no flow of current, okay, or we can say as a total, as a net, that there is the net current is zero, because the this is the flow of the current, and which is very it can be in the range of the nanoampere, in the range of microampere. It can be in the range of milliampere if the diode is used for the power sides, for very high voltage and for the very high current flow, or the diode itself is a very big size. Then there could be possible that that the is can be in the range of the milliampere, but generally it is in the range of the microampere or nanoampere. So if there are any question, please let me know. So in these slides, what we have seen here, that we discussed about the forward bias and the reverse bias, and during this study, we also discuss step by bit by bit in pieces the contribution, the what is the minority charges and what is the majority charges in the p type and the anti-material, and the how these minority charges and the majority charges contributes in the flow of the current through the PN junction. Hopefully you understand. Class is over. If you have any question, please you may ask. Take care. Bye bye. Allah Hafiz.